Hi to all, welcome to Algotech Programming Concept. In this video lecture, I am going to discuss need of red-black tree and properties of red-black tree. In next video lecture, I will discuss the various cases which are used to get balanced tree. So in this slide, you can see that there are four keys: 41, 38, 31, and 12. If we use binary search tree to insert these keys, so we will get left skew binary search tree. If keys are inserted in left skew binary search tree, or if we are getting right skew binary search tree, then the complexity of insertion, searching, and deletion will be order of n, and we can improve this complexity from linear order of n into logarithmic, which is log n base 2, by applying the AVL tree or red black tree. In red black tree, we will use some color scheme. We will change color scheme, and we will get the balance tree. So in this red black tree, you can see that node G, it means that if this is node G, and P of G is parent of this node G, and PPZ is grandparent of this node G. G is 12 here. So G is a newly inserted node. P of G is parent of node G, and PPZ is grandparent of G. And this node 41 is uncle of G, because and this is P of G, and this is uncle of this node 41 is uncle of G. So in this way, we can reduce the height is equal to 3 into height is equal to 2 if we use red black tree. So searching insertion deletion operation will be faster as compared to left skew binary search tree or right skew binary search tree. So that is a need of red black tree, that we can improve the complexity of complexity of left skew binary search tree or right skew binary search tree into order of log n base 2 by using AVL tree or red black tree. So in the next slide, I am going to discuss the properties of red black tree, which are very useful when we will convert when we will get balanced tree. So in red black tree, newly inserted node color is red, and if it is a root node, then color will be black. So we will make color black of this node 41. Okay, so because this is a root node, so the color of root node will be black. So node of the color of any node may be red or black, but the color of root node will be black. Second property is over, and the third property is that the children of red node must be black node. Here you can see the 19 is a red color node, so the children of this 19 will be black always, but the children of black node may be red. This is 38 is a black node, so the children of black node may be red or black, or black means 41 has two children here. There are, you can see that there are two children, and if any nodes is missing its any children, so we will assume that there is one nil children here. So we can assume that there is a nil children, and the color of nil child is black here. Okay, so this is a fourth property, that all leaf nodes are colored with black. So we can see that all the leaf nodes are colored as black, and if any nodes child is missing, as I have discussed that node number 12 missed its right child, so we will assume that it has nil child in that place and always colored black. So nil child will always color black, and we will assume in the absency case of any child of node. And the fifth property, that is a most important property, that is known as black height property of node X. So that is property says that every path from any node X to its descendant leaf node, the number of black nodes will be same. So from node number 38 to its leaf node, okay, we can see that there are several paths. If we choose any path, okay, there are many paths, you can compute here. If you choose any path, so the number of black nodes will be same. So if we choose 38, 19, 12, 8, and then last nil child, so here we are getting two number of black nodes. Okay, so we will not include x1. The color of x1 will be not included here if we start traversing from node x1 to its leaf node. If we choose from node 38, 41, and then nil, so 41 and nil are black color. If we choose from node number 38 to its leaf node in the right direction, so there are two number of black nodes. If we choose from node number 19 to its leaf node. So what how many numbers of black nodes will be there? If we choose from node number 19 to this path, node number 19, 31, and nil, so there are two number of black nodes. Then if we choose from node number 19 to to eighth descendant, to the last leaf node, 19, 12, 8, and nil, so there are two number of black nodes, 12 and nil. So there are several paths from any node to its descendant leaf node, and in every path we will get the same number of black nodes. That is the black height properties of node X in red black tree. So, and in red black tree every node has color field and key. What is the key inserted? Left pointer, right pointer, which are pointing to the child and its parent also. So in the fifth property we can compute the number of black nodes from any node towards the leaf node, and I have written it here. So the black height property of node number 41, 41 is here. So we are there are two paths, and the number of black nodes are 1. So nil child is always black. And from number 12, there are how many paths? You can see that there are three paths: 12, 8, nil, 12, 8, and if we traverse right side, then we will get nil child. And the third one is that directly we are getting the nil child here. Okay, so there are three paths, and the same number of black color nodes is are 1 here. So you can, in the next slide, I will discuss that what are the various cases which are used to get the balanced tree in red black tree. Thanks for watching.